So we're doing an entire chapter on quadratics. An entire chapter. All of chapter 2 is quadratic. So we start with our family name, quadratic. Then we're going to write the ordered pairs that are the parent function for quadratic. And we're going to do 7 of them. So we're going to start at -3 for x's. -2, -1, 0, 1, 2, 3. And then remember, quadratic is x squared. So if you forget these y values, the x's are easy. They're just any numbers you want in order, makes it easy. If you forget the y values, what do you do to the x's to make the y values? You square them. So what's -3 squared? 9. What's -2 squared? 4. -1 times -1. 1. 0 times 0. 1 times 1. 2 times 2. 3 times 3. So if you forget, you just square the number, and then you have your parent function. You can plot the parent function. I like to start in the middle. You can plot it in any order you want, but I like to start in the middle because when I go to the right one, or if I go to the left one, both of them go up 1. So if I go right 1, I go up 1. But it's symmetric, so it does it to both sides. If I go right 2, then I go up 4, because 2 squared is 4. And it's symmetric, so it does it to the other side too. If I go out 3, then I go up 9 from that center point. So from the center point, I'm going out 1, up 1, out 2, up 4, out 3, up 9. And then we have our parent function, which we did last chapter a little bit. We're going to focus heavily on it this chapter. Does anybody like patterns and intrigued by patterns and puzzles and stuff like that? And some of you, I like patterns. I think they're very interesting. Here's a pattern that I think is very interesting for this. I'm just going to start at 0 because this is symmetric. It goes, it's the same numbers if you go, if you count up or count down, it's the same numbers. But I'm going to start at 0. From 0 to 1, I would add 1. And then from 1 to 4, what would you add? From 1 to 4? 3. And then from 4 to 9, you would add 5. What is the next square? If I had 4 and then 16, what would that difference be? 7. Do you see a pattern at all? If I had 5 and 25, what would come next? Plus 9. You're so good at that subtracting there. Do you see a pattern? It's not a coincidence. This is for real a pattern that the perfect squares always go up by odd numbers. So when you're graphing and you plot them, the difference between these dots up and down, the range between the dots, between the points, that should be 1, that should be 3, and that should be 5. And then for the next one, it should be 7 more. That's what gives it that curve. Just in case you're curious about patterns, anything that helps you remember those points is going to be helpful. And to really help you remember those points, you see how many graphs I have in there? I'm going to stop talking for a moment. Every single one of these graphs we're about to do has a parent function that is f of x equals x squared. And you are going to graph that parent function. You're going to dash it on every graph. You're going to plot the points and use dashes to draw the parent function. And I think there's like 22 of them. And I'm going to stop talking for like 2 minutes. And you are going to memorize those points because you're going to do it like 22 times. So you're going to commit it to long-term memory. Don't feel like you need to do anything extra yet. Just do the parent function on every single graph. That parent function on every single graph. Back to this original, there's some vocabulary that we're going to start adding on to quadratics. Before we do anything else with them, we're going to start talking about vocabulary. One thing I've already said is the parabola, the quadratics, are symmetric. Every single one of them is symmetric. So if you find like half of the numbers, you actually found all of them. Because these numbers will always be symmetric with those up there. Always symmetric. And so if you look at the graph, there's always this reflection line where both halves are symmetric over. You see where that line is right now? This line right here? That line is very important and it's used in the future here. So we're going to give that line a name. It's called the axis of symmetry. That line is called the axis of symmetry, and I will probably at some point abbreviate it AOS, because axis of symmetry is a lot. But that's what it stands for, the axis of symmetry. It's that line that is right in the middle of the parabola, right in the middle of that quadratic. That axis of symmetry for this particular example, well, for any of them, is a line. I've just said it a couple times. It's a line. It's a line of symmetry. So we write that as an equation. We write it as x equals, and then you have to think for yourself, every single ordered pair on this line, what is the x value for every single ordered pair on that line? If I wrote any of those ordered pairs, what's the x on that line? Stuart, give me an ordered pair on that line. 0, 3. What's x?
0.
Correct. Jessica, give me a different ordered pair on that line. 0, 5. What's x? So now, everybody answer me. What's x always on this line? 0. So my equation for my axis of symmetry is x equals 0. If you write on your paper just 0, it would be wrong. It is the equation of the entire line. It's every ordered pair where x equals 0. So that's the axis of symmetry. The next thing that is important is this point, this turning point on the graph, the point where the graph goes from decreasing to increasing. Or if there's a reflection, it'll go from increasing to decreasing. It's the turning point. It has a special name. Anybody know it already? Nobody knows it? You know it? The vertex. That is correct. That is the vertex. And for this particular graph, where is our vertex located? It's an ordered pair. Where is it? 0, 0. That's for this graph. And then the third thing that's going to be important to find, and we've already sort of talked about these, is the y-intercept. The y-intercept is always on the y-axis where the graph passes through the y-axis. It's always where x equals 0. And in this particular graph, where is x equals 0? What ordered pair? 0, 0. That's for this graph. It'll change. You'll see. So what we're going to do is we're going to go through a bunch of examples. And we are going to find the equation. We're going to write the transformation. We're going to graph it. We're going to write the domain. We're going to write the range. We're going to find the vertex, the axis of symmetry, and the y-intercept for all of these. You see, all that information I've really abbreviated. You see what I'm like, as for equation. So we're going to do a bunch of them together. At any point that you feel like, okay, I got this, she's going too slow, come work ahead. So the first one starts out with g of x is equal to f of x plus 3. Does anybody remember what f of x is? It is a function of x. What is it? And it is y. Whoever said y, it is y. But for this particular example, what function is our f of x function? It is the parent function. Which is our parent function for this one? X squared. Excellent, excellent, excellent. Good job, guys. That is the x squared function. So I look here and I see g of x is equal to our parent function plus 3. So our equation is g of x, I want to write it in blue, sorry. Oh. Here we go. G of x is equal to, our parent function is x squared, plus 3. This is what we did in the last chapter, but some people still are having trouble with this, so we are reviewing it more. And we're going to do this almost the entire year, reviewing this transformation stuff. So if you're like, I didn't learn it the first time, we're on the next chapter, it's not going to work that way in math. Like, you have to learn it because we're going to keep seeing it over and over and over again, just with different equations. All right, so we've got g of x equals x squared plus 3. What transformation is plus 3 from our parent function? What's that do? What? Up 3. Translate up 3. Perfect. 3 units. Translate up 3 units. So if we go to our graph, and we already have our parent function there, if I take every point that I plotted and just go 3 higher, I should have my new function. So every point I plotted, move it up 3. 2 of them don't fit on the graph because they're too high. And now we review domain. Domain is what x's I'm allowed to plug into the equation and square. Domain visually is how far to the left and how far to the right my graph will eventually go. Who knows the answer for domain? Read.
All real numbers.
All real numbers. So you can write all real numbers, or if that is too much work for you, you can use the appropriate abbreviation for all real numbers, which is that fancy R with the 2 lines. You don't make up your own abbreviation. So all real numbers or the fancy R. And then the range is how far up and down. It's the y value. So the range has some restrictions on it because this graph goes down, but then it comes back up. It doesn't go all the way down forever and ever. So what is the lowest point on this graph when we talk about the y value? The lowest point is what? 3. So my graph, the y values begin at 3 and then they go up. So we'll say y is greater than or equal to 3. And then we look and we need to find our vertex. Our vertex is that turning point on the graph. Right now it's the lowest point. What is that turning point for the vertex? 0, 3. That is our vertex. And then our axis of symmetry is the line in the middle of the parabola. It is always x equals. And the other thing it is always the x number in the vertex. It is always the x part of the vertex. So what is the axis of symmetry for this one? X equals 0. And on the y-intercept, where does the graph pass through the y-axis? At what ordered pair? 0, 3. Before I do another one, is there something I need to explain further up here? Is there any questions you have on this first example? So the next one I'm going to do is 3. So I'm going to skip over 2, and if you're working ahead, you already did some of 2. Excellent. But I'm going to go to number 3. And we're going to do the same thing again. So this one says that 3 is the function's name is p of x, and it is the parent function take away 3. So we're going to write the equation. P of x, what is our parent function? X squared take away 3. So what transformation is that? Translate down 3 units. Good. So graphically, what am I going to do to each point? Go down 3, each point on the graph. All right, and then the domain is left, right. It is what numbers I'm allowed to square. So how far will this graph eventually, if I keep drawing, go? All the way to the left, all the way to the right? So what is that? All real numbers, or fancy R. The range is how far down to how far up. So how far down on the graph are we going? Down is the y value. How far down is the y? -3, and then from there it goes all the way up. So we'll say that the y's are greater than or equal to -3. Then we need to list our vertex. So we look at the graph, where is that turning point on the graph? Where's my vertex? 0, -3. The axis of symmetry is that line that passes through the vertex, that vertical line that passes through the vertex. So it's always x equals, and it always has the x value of the vertex. So x equals 0. And then our y-intercept, where does the graph pass through the y-axis? 0, -3. And then I'm going to do 5 next. At any point that you notice patterns and you feel like you can do some of the evens as I'm doing the odds, I would highly encourage that. The more practice, the better you're going to get and you're going to remember more. So if you're noticing any patterns, and if you're not sure if it's a pattern, ask. Number 5. This time we've got a of x, and it says that we take the function, but instead of x, instead of f of x, we make it f of x plus 3. That means we replace x with parenthesis x plus 3 in the parent function. You replace x with parenthesis x plus 3. And you did have that on that last test. So our new function is a of x equals. So if I pull out the x and I replace it with parenthesis x plus 3, it's going to look like that. X plus 3 quantity squared. So I took out the x, replaced it with parenthesis x plus 3. And it's still squared. Now what kind of transformation is it if in parentheses we have x plus 3? Translate. Left, where, how much? 3 units. So on our graph, every ordered pair, just move them to the left, 3 points, 3 units. That was a little bit off. Why this prints out. I must have moved something. I'm sorry. It's not good. I gotta redo it. Okay. While I'm redoing it, you guys think that I actually go to every ordered pair and count 3 dots over? You think I count 3 points for each dot? You think I'm doing that? I'm just taking the shape because I know it's out 1, up 1, out 2, up 4, out 3, up 9, and I'm finding that vertex, I'm just going off of that vertex. That's what I'm doing. But if you need to count 3 over from every single point, it's fine. That's just not how I'm doing it, because I have it memorized. So our domain, how far to the left and how far to the right does it go if we extended this forever? Domain? All real numbers? Gosh, that seems like a pattern. And then our range is from down to up. So how far low does it go? The lowest y value. You gotta think like ordered pairs. What's the lowest y value? 0. So our range is y is greater than or equal to 0. Our vertex is what ordered pair? -3, 0. Good, Emma. And whoever else was talking good. Axis of symmetry is the line that goes through the vertex. So it is the x value of the vertex. X equals -3. And then the y-intercept is always 0, comma. What is it for this one? What is it, Zena? 9. You just have to look at your graph for that one. Okay, we're going to do the next odd question. So if I'm going too slow for you, please feel free to, work ahead. So if you get used to writing -3 and not x equals, you will not remember it. And I will mark off, if you do not have your axis of symmetry as x equals, you will miss it. Because I'm going to say it like 20 times today. I didn't walk around to see who is not writing it correctly on your paper. I'm trusting that if I write it on the board, you're doing it too. So I'm going to do number, what am I on? 7. So 7 says f of x minus 3. So that means wherever I see an x, replace it with x minus 3. So c of x is equal to parenthesis, x minus 3, close parenthesis, and then that is squared. Because remember, my f of x is x squared. Wherever I saw an x, replace it with parenthesis x minus 3. What does x minus 3 tell me to do to the graph? I'm going to start calling on people, okay? Carly, you know what that says, the minus 3? Translate right 3. Wonderful job. So you can take every ordered pair and count over 3, or you can move your vertex and then just draw the parent function from there, which is what I do. Remember, we're doing all this in class today so that you have it memorized when you leave this room. Hopefully. Fingers crossed. Domain. How far to the left? How far to the right? Timothy. All real numbers. Good. Is that a guess or you knew that? Excellent. Is that from a pattern or did you have to think about the pattern? Good. That's one thing that's awesome about math is once you figure that pattern out, the pattern happens over and over again. Range, from low to high, from low to high. This one might be a trickier one. From low to high. Jacob, you know that? What? Yeah. How do I don't just write 0. Y is greater than or equal to 0. Excellent. The vertex for this one, the vertex, Duncan, do you know the vertex for number 7? Vertex?
3, 0.
3, 0. Yep, you are correct, sir. Axis of symmetry. Ellie, do you have the axis of symmetry? X equals 3. Very good. And then the y-intercept. Matt, do you have the y-intercept?
39.
Not 39.
0.
0. Should be 0 because it's going to be on the y-axis. So the x has to be 0. And then it's at 9. Very good. All right, next one is number 9. So this would be one thing that I feel like some people are still a little bit unsure of after writing some of those tests. This negative symbol. Anytime there's a negative, that means there's a reflection. It means there's a reflection. A reflection. If you see a negative symbol, reflection. Then we got to figure out which one it is. So here we have e of x equals negative f of x. You guys probably have an extra parenthesis, don't you? You have an extra parenthesis, don't you? I added it in and I forgot to change my notes, but so yours is better than mine. So e of x, this says to put a negative on the outside of the function. So we would be doing negative outside of the x squared. But when I simplify that, if I do negative times an x squared, that's just negative x squared. So I don't actually need those parentheses for the final answer. And that is a reflection. So we're going to reflect, and we say in the. Now, which way is it a reflection, though? Who knows this one? Yes, in the x-axis. So that means from here we're going to reflect vertically down because it's going to go over that x-axis. So the 0, 0 is still there, but all the other ones we're going to reflect down. It's going to look like a like a pond where you can see the reflection on the top and the bottom. A lake or something. And then I want to point something out to you that's, I don't know if it's helpful or not. Let's point something out to you though. Right here, in the parent function, what ordered pair did I just make red? The parent function. 2, 4. Now the same point in my new function that's reflected is what ordered pair? 2, negative 4. So that negative sign affected which variable, the x or the y? It affected the y, it multiplied the y. A reflect in the x-axis changes the sign of the y values. So the y's are multiplied by negative 1. That's going to be important in a little bit. Domain. Domain. Brandon, do you have the domain?
Which,
For any of them.
oh,
All real numbers. But for number 9, do we have the range? Brooke, number 9, do you have the range? Excellent. We didn't even do any like that yet, so I'm glad you came up with that. Y is less than or equal to 0. This time it's below 0. Then our vertex is at 0, 0. Our axis of symmetry is x equals 0, and our y-intercept is at 0, 0. Okay, if you have no questions and you're ready to go on, I'm going to do number, what's next? The next odd one. I can't see what number I'm on right now. I'll do 11. 11. So we have f of negative x this time. N of x is equal to f of negative x. If it's f of something, that means replace x with parenthesis negative x. So instead of f of x equals x squared, we have to replace x with negative x. So n of x equals parenthesis negative x, we'll close the parenthesis squared. This is a reflect in the, Aiden? Yes, reflect in the y-axis. So if I come over here to my graph, and I have the ordered pair 2, 4, and I reflect in the y-axis, where is that point now? Anybody know? Negative 2, 4, yeah, it's right here. But if I take negative 2, 4 and I reflect that one in the y-axis, what's happening when I take this and I reflect it in the y-axis? Isn't it the exact same graph? Because, you know why? If I took this equation and I said negative x multiplied by negative x squared, I multiplied negative x times negative x, what's negative times negative? Just positive. It's the same equation, right? It doesn't always work out like that, but since there's no other transformations on it, it's just that exact equation. So we've already filled out this information earlier. I'm just going to skip that, and we've already finished all that information earlier on a different, like on the very first example. So I'm going to keep going. I want to do 12. I don't have it written up here, but you guys have it on there. I want to go over 12. Let's do 12, and then we'll take a break, okay? Let's do 12. I just need to copy it down. Wait, what's the variable? R. Okay, did I copy it right? If you are working ahead, you probably did 12 wrong. Just to get you've already said it wrong, probably. 12 has something very unique that none of the rest of these examples have, but I want to tell you about it now. If we have, well, we've got to write the equation first. Equation. R of x equals, so wherever I see an x, I'm going to replace it with parentheses, that. So I'm going to have parentheses negative x minus 3 close parentheses squared. There is this special case where if I have a number in front of the x and I have a number translation with the x, if I have both, I have to do what's called factoring. I need to factor out the -1. I have to factor out that -1. It's not going to go outside the parentheses, but it's going to come out of that 3. I'm going to show you what I'm talking about. Wherever you have room, you know, put it on. This is the only one that's like it on here. But this is a special case. So when I factored out, I still have these outside parentheses squared. This is not going to affect the squared at all. It just affects what's under here. So I'm going to factor out this -1. And factoring is the same thing as the distributive property, it's just backwards. So instead of distributing, we're factoring out. What operation is distributing? What operation is distributing? That's multiply. So then what's the opposite of multiplying? What would it be to factor it out? What's the opposite of multiplying? Divide. So I'm going to divide out that -1 from both terms. So when I divide out the -1 from x, I get x. When I divide out the -1 from the -3, I get +3. So see how my negative did not come out outside of the parentheses? It's still inside. It's just separated from the 3. I had to pull it out of that. So when we talk about transformations, there's 2 transformations for this. What's our first transformation? Help me out. Is it a 3 or a 5? It's a 3, right? Okay, sorry. What's my first transformation that I'm pointing to right now? It is still inside the squared. It's reflect in the y-axis. And then our second transformation, that's our first transformation. Our second transformation, still inside the squared. Translate three units left. Okay. Now I know that I didn't leave a whole lot of space on there, so when you do this next step, you might want to just squeeze it in over here. There might be a little room over there. I'm going to show you what we're going to do later in the class. I'm just going to show you right now before we take our brain break. What we're going to do is that you can do this by just eyeballing it and just like saying it's a reflect in the y-axis, it's going to do this, and we're going to go right through. You can do that. But I'm going to have a backup plan for you. I want to show you how to do it without thinking. Like it'll work every single time. So what I'm going to do is I'm going to make a table, and my table is, so for spacing wise, my table is going to have 4 columns. So you got to kind of write small, okay? You can put it wherever you can fit it around this question. It's going to have 4 columns though. The middle 2 columns are x and y. And I'm going to put my parent function in the middle 2 columns. So -3, -2, -1, 0, 1, 2, 3. 9, 4, 1, 0, 1, 4, 9. So I put those in there. Oh gosh. This Criswell's not helping you very much. That's actually rude. You don't have to erase. You might have to write on your graph a little bit. It's okay if you write on the graph. I promise it's okay if you write on the graph. I lied. There are 4 columns. I just put them on the wrong side. There's 2 on that side. You can just write on top of your graph if you don't have room. We're not going to use that side of the graph anyway. Okay, so when we do our reflect in the y-axis, that affects which variable. If it's a reflect in the y-axis, we're going, which variable does this? Which variable goes left to right? What does it matter? The x. The x goes left to right. So when we reflect in the y-axis, we are multiplying the x's by -1. So you look at your x's and you multiply all your x's by -1. 3, 2, 1, 0, -1, -2, -1. You always multiply before you add or subtract. You always multiply before you add or subtract. So that's why we did -1 first. Our second transformation is 3 units to the left. So is that going to be adding or subtracting 3 if we go to the left? Subtracting 3. We go to the left. Left is subtraction. In the equation it's add, right? In the equation it's add. But we actually go to the left. Subtract 3. So we're going to subtract 3 from all the x values. So when you go to graph your new function, you want to use the most recent x and the most recent y. So did we change the y's at all? So we're going to use those y's, but we changed the x's twice. So we're not going to use either of these x's. We're going to use the red x's and the black y's. So I'm going to graph 0, 9. -1, 4, -2, 1, -3, 0, and then the rest of them that are. table correct, it should be a reflection in the y and then left 3 from the original function. So that's kind of a taste of what we're doing today. We're going to be doing composition functions. We're doing multiple transformations and graphing them. We're going to take a brain break and get our mind like out of this for a moment, and then we're going to come back and do a little bit more with it. Okay? And then any extra time you guys will be able to start your assignment. So when you're done copying this one down, stand up, don't pull out your phone. Stand up, start stretching out your legs, we'll play a game. But stand up until I'm ready, people to copy it down. I gotta pause it. If you're still copying, it'll be right up there in 1 second. I'm gonna pause it. Okay, so we're this whole chapter talking about quadratic functions. And the U shape itself, I've said the word parabola a few times, but there's the word parabola, if you want to spell it correctly, parabola. That's what the graph itself is called. So like a linear equation is called a line. A quadratic equation we call a parabola. And there is a form that we have been using for parabolas and for other functions, and it looks like this. And that's the form that we find all the transformations in. And this form does have a name in when it's in the quadratic function. This form is called vertex form. And that's because the vertex comes from the translations. So where the vertex is normally for the parent function, where's the vertex normally for the parent function? For f of x equals x squared, where's the vertex? Help me out. At 0, 0. If there was a translation, I don't know, 2 to the right and 3 up, where would our vertex be now? If it was 2 to the right and 3 up, it would be at 2, 3. Like if that was my translation, then that's where my vertex would be. And you would get that translation from what's in with the x and what's outside. That would be your horizontal and vertical transformation. So that's called vertex form because it helps you find the vertex quickly. But we'll talk more about that later. Today we're just going to graph. So I'm going to go to example 1. If you guys can go find example 1. Graph your parent function. You don't necessarily need the table yet. Graph your parent function. And then we're going to describe the transformation. So go to example 1, graph your parent function, and then look at the equation and describe our transformation. Parent function that you've memorized. So you graph your parent function and we look at the equation. It's got x plus 4 in the parentheses. What does that mean? Timothy, what's the x plus 4 mean? Translate left 4. And what's the minus 1 mean, Natalie? What's the minus 1? And translate down 1 unit. So for my vertex, I'm going to go move my vertex left 4, down 1, and then recreate the graph. Left 4, down 1, and then recreate my parent function. Or you can move every single ordered pair left 4, down 1. If you're not sure, you can move every single ordered pair left 4, down 1. And this works because there's no stretch or shrink. This works because there's no stretch or shrink. Or reflection. It's just translating. It's just sliding it over and down or up and right or something. So there's 3 student examples. I want you to graph your parent function, write the transformation, and move the graph. Let's see how you do. I'm going to pause the video, make sure you help me remember to unpause it. So I have the answers. They're a little light, a little hard to see, but I do have the answers up here. The first one, translate 3 to the right, and I have the graph. Our vertex is where? Just call it V. What's our vertex at? This one was actually one of the ones we did today, earlier too, wasn't it? This vertex point is, help me out, 3, 0. So our axis of symmetry, our AOS, is x equals 3. It's always the x part of the vertex. It's always passing through the vertex, so it's always the x part of the vertex. And then our y-intercept, 0, 9. Yeah, that one we did earlier in class. The next one, our vertex, 2, -2. So then our AOS, our axis of symmetry, is always x equals, and what does x equal in our vertex? 2. This is the one, oh no, our y-intercept works out for this one, never mind. What's our y-intercept? 0, 2. Right there. This one, our y-intercept, might be a little tricky. Okay, so our vertex for the third one, our vertex is -5, 1. And this is vertex form, so you can see the -5 here and the +1 there. It's vertex form, so there's our vertex right there. You just have to remember x is always opposite. And then our axis of symmetry, it's always the x part of the vertex, x equals -5. And it's the y-intercept that's a little tricky, it's not even on the graph. So for the y-intercept, we know that the y-intercept is when x is equal to 0. So what we do to the equation is we plug in 0 for x. So our equation is g of x equals x plus 5 squared plus 1. We make g of 0. We plug in 0 for x. 0 plus 5 squared plus 1. And remember g of 0 or g of x, that's just the same thing as saying y. So we don't do anything to that side. We just simplify the right side. What's 0 plus 5? Squared. 25 plus 1, 26. So our y-intercept is at 0, 26. So any point where you couldn't find the y-intercept, we're going to keep practicing that, but if you couldn't find it because it's like not on the graph, that's how you find it. You plug in 0 for x. Okay, and then our last few examples, we're going to do stretches and shrinks and reflections. And these, we're going to practice more again with the table. So when you graph your parent function, also write the table. So graph your parent function, hopefully it's memorized. And then the table, the x's go from -3 to 3, the y's go from 9 to 9. But they're squares. And then you're going to have to sort it. So I'm going to put it like we're going to have to, well, actually this one's okay. But in the future, we might have to put stuff on either side. This time, you're only going to put it on that side, so you'll be fine. So we're going to make our table, and then we need to write down our transformations to know what to do to the table. So anytime we have a stretch or a shrink, we're going to want to use a table. Just telling you that now. If we have a stretch or a shrink, you're going to want to use a table. Here, do we have a stretch or a shrink? Yes, we do. We have something. So remember, the negative sign. Is the negative sign a stretch or a shrink? No. The negative sign is alone by itself what? Reflection. So what's this one? I reflect in the x-axis. And then the 1/2. Is that inside parentheses or outside? That's outside. It's not in with the square. So it's vertical. So 1/2 is a vertical what? So if it's vertical, it's just kind of what you think by looking at the number. It's not opposite. So 1/2 makes things smaller. 1/2 is a shrink, vertical shrink. If it's above 1, then it would be a stretch. So vertical shrink by factor of 1/2. So since negative 1/2 is multiplied by the x squared, because reflect in the x-axis and vertical shrink are both vertical transformations, we're going to change our y values. We're going to be changing our y values. Both of these are vertical transformations. So we change our y values because they're vertical. It's both a negative and a 1/2. We can do that in one step. Multiply by negative 1/2. You don't have to multiply by negative 1, then multiply by 1/2. You can just do it all at one time. So you're going to take all your y's and multiply by negative 1/2. So we get negative 9/2, negative 2, negative 1/2, 0, negative 1/2, negative 2, negative 9/2. Notice the symmetry. You really have to do the math for only half of them because it's symmetrical. We always graph the most recent x and the most recent y. So since we changed our y's, we don't graph those y's. We only graph the most recent ones. So I'm going to graph the ordered pair negative 3, negative 9/2, which is negative 4.5, by the way. Negative 3, negative 4.5. Then I graph negative 2, negative 2. I graph negative 1, negative 1/2. 0, 0. 1, negative 1/2. 2, negative 2. 3, negative 4.5. And parabola it. Make it a U. We're going to do that again with the next example. So graph your parent function, write the table. Leave space to change numbers in the table. The next one, graph the parent function, write the table for the next one. I still have mine up, so if anybody's still copying it, they can do it. But if you're ready to go on for the next one, draw your parent function, write the table. It's the same table every time. It is the parent function you write in your table. So do you know where I would have got this? Do you know where I got that from? Right, so we're not using the old y values, we're using the new y values and the original axis. So I'm just grabbing those. So if I go too fast, because I saw you like just copying the picture, you can just there. Okay, so I have my table. These are my original parent function xy's. Now we need to figure out the transformation. So inside the parenthesis, I see a 2. What does that mean if it's inside? It's horizontal. And if it's horizontal, it's always opposite. So I have a horizontal, if it's 2, is that going to be a stretch or a shrink? It's always opposite. So if it's 2, it's a what? Shrink, right, shrink. And then what is our factor? It's always opposite. By factor of half. So we get that out of the 2. And then what's the plus 1 tell us? Translate where? Is it inside parenthesis or not? Inside or outside? Outside. So what is it? Up. So for my table, since I have a shrink, I am going to use a table. And is my shrink going to affect my x values or my y values? What does horizontal tell me? X or y? As a class, what is horizontal? X or y? X. So in our table, we will change our x values by a factor of 1/2. We will multiply our x's by a half. It says 2 in the equation because horizontal is always opposite. So you multiply by half, we get -3/2, -1, -1/2, 0. 1/2, 1, 3/2. By the way, 3/2 is 1 and 1/2 if you're graphing now. And then translate up 1 unit. Up means vertical or horizontal? Vertical. So is that the x or the y? That's the y. So on our y side, we will add 1 to all of our y values. 10, 5, 2, 1, 2, 5, 10. Oh, and they're symmetrical. And you always graph your most recent x's and most recent y's. So I will graph -3/2, 10, which is -1.5, 10. -1, 5. -1/2, 2. 0, 1. 1/2, 2. 1, 5. 1.5, 10. So we have a horizontal shrink. It got skinnier horizontal-wise, shrank horizontal-wise, and moved up one from where the vertex was. So there's 3 for you to try. There's 3 for you to try. I would start by writing the transformation. And then I would draw the table. Or draw the table, then write the transformation, one or the other. Just going to pause this. I just want to make sure that we are practicing the right way. I don't want you to practice it the wrong way because that's the way you're going to remember it if you practice it wrong. So when you have a 1/3 and it's inside the parentheses, you write horizontal. I know it's horizontal because it's inside. And then you think horizontal is always opposite. So if it's 1/3, that usually means smaller, but it's horizontal, so it's going to be stretch because it's opposite. And by factor of, so we look and it says 1/3, but we have to write down the opposite. What's the opposite of 1/3? 3. So that's a horizontal stretch by factor of 3. Well, and that's the only thing done to it. So then we have our table. And what column am I going to change, the x's or the y's? If I wrote down horizontal, what am I going to change? X's. If I wrote horizontal, that's x. So I'm going to multiply my x's by 3, by the opposite of 1/3. So all my x's get multiplied by 3. And you always graph the most recent. Whoops. Always graph the most recent. Sorry, I didn't graph my parent function, but timing-wise, trying to hurry. So I will graph negative 9, 9, negative 6, 4, or yeah, negative 3, 1, 0, 0. This table is something that we're going to continue to use throughout Algebra 2 also. Like everything we do in here is going to happen over and over and over again, so that when you leave here, you know it. Just going to do it in different ways. We don't like the table, I'm sorry. So there's the answer. I have the answer up there. Same thing. Okay, the next one, what are our transformations? Where is that 3 located? Is that horizontal or vertical? 3. Vertical. So vertical is normal. If it's 3, is it going to be a stretch or a shrink? Stretch. By factor of, it's vertical, so nothing changes, so factor of 3. And then we also have a minus 1, and the minus 1's inside the parentheses, so where's that going to go? That one's horizontal, so it's going to translate opposite, so it's going to translate to the right. One unit. Going too fast. So anything that we're going to change in the table, you have to think about if it's vertical or horizontal. So I read vertical stretch by factor of 3. Is that going to be x's or y's? Vertical. That's the y. So on my y side, I will multiply by 3. On my x side, translate right 1 unit is adding 1. Right is plus. So I'm going to add 1 to all my x values. My x values, there's a pattern with those too. You just add 1 to every single one. They're still in order. Then we graph the most recent x and the most recent y. Negative 227 doesn't fit on the graph though, so I'm not going to graph it. Negative 112 doesn't fit on the graph. It's just above it though. I could probably sketch that. 0, 3, 1, 0, 2, 3, 3, 12 is just right up there. And then 27 is nowhere near. And then you should have your parent function. I just didn't do it because of time. And then make a table because we're going to do the last one together, and that's the last example for today. Make a table. Grab your parent function. That last one. Write your transformations if you know them already. Okay, the transformations. What's the negative mean? Reflect in the x-axis. Reflect in the x-axis. Is that vertical or horizontal? reflection. Is it going to affect my x's or my y's? Is that vertical or horizontal? Just like make me look stupid. Is that what's going on up here? That is a vertical, yeah. I'm just kidding. I like to look that way. So it is vertical. So we'll think about that when we fill out our table. What's the plus 3 in the parentheses tell us?
Translate left 3.
Translate left 3. And what's plus 2 tell us? Up 2 units. So in our table, we always do multiplication before we do adding or subtracting. So we're going to do the multiply by -1 first. But does that go to my x's or my y's? The reflection, is that to the x's or the y's? If it's vertical reflection, we multiply the y's by -1. So all my y values, -1. Just changes the signs. Our x's translate left 3. Is left subtracting or adding? Left is subtracting 3 from all of our x's. And then we have to add 2 to all of our y's. And the y's are symmetrical, so they shouldn't take too long to do. You graph the most recent x and the most recent y. Did that one have a stretch or a shrink? So it should be just the parent function reflected and translated. Should still have that out 1, down 1, out 2, down 4. It should have that same pattern. All of the questions that you are doing for your assignment are what we just did, where you're going to write the transformation and you're going to do graphs with the parent function. So I have graph paper that you can just do like your work on and then graph it right next to it. So you won't need your own paper. But it is in the book. So you can get to the book by getting on Big Ideas Online and opening the book. You can take a picture of the pages in the book before you leave, or everybody checked out a book. So you should have a book. I'm going to put up, I'll put up the numbers, but then I'll put up the actual book so you can start working on number 3. You don't have to go grab a book, like it'll be up there. You can just look. So we don't have to take time out. And I can't remember how many graphs you need, but you need 2 pieces of paper. Otherwise, I guess you're going to have to go online and print some more of this out. It's on Canvas, the graph paper is. You'll need 2 pieces of paper for the graphs. I just don't remember how many exactly. But it's more than 8. That's how many one is on one paper. I did put more graphs on Canvas. If you screw up big time and you need more because you did it in pen, on Canvas there's more graphs. Take 2 pieces of graph paper, 2 pieces. Take 2 pieces of graph paper. Tell me if you didn't get 2 if I counted wrong. You need 2 pieces of graph paper. Let me know if you didn't get 2. So the assignment is page 52, 3 to 5. 7 to 11 odd, so the odd part is only the 7 to 11. The 3 to 5 is all. 17, 20, 21, 24. I'm going to stop the video and then put that right back up. Nobody needs to hear me talking now.